Yes, sir. We are in live now. So, very good morning to all the participants. And it is a great pleasure to have you all here for the Knowledge 4.0 webinar series, which is one of the unique initiatives of Chennai Institute of Technology under the guidance of our Honorable Chairman, Sri P. Sriram, a successful first generation entrepreneur, a well known industrialist, and managing director of MK Group of Companies. Under Knowledge 4.0 series, we have been conducting webinar series such as Technical Webinar Series, Research Webinar Series, Career Guidance Webinar Series, Alumni Webinar Series, and Innovation Webinar Series. And today, we have Technical Webinar Series titled Fourth State of Matter and its Applications, which is going to be handled by Dr. Ramraju, Intel Corporation, USA. So, Chennai Institute of Technology was established in the year 2010 by our Honorable Chairman Sri P. Sriram, and now our institute is being ranked within top 10 institutes among private engineering colleges in Tamil Nadu. And it is a great pleasure now to introduce our guest speaker, Dr. Ramraju, with 10 years, more than 10 years of R&D experience in developing plasma material process for semiconductor memory, solar and glass industries. And experience worked with various semiconductor processes such as dry etch, thin films, and photolithography. Experience in leading a group of process engineers in HPM PV industries and strong knowledge and understanding of the fundamentals of plasma physics, plasma characterization, plasma materials processing, and vacuum technology. Sir has completed his PhD in Bharatiyar University in the year 2000, and he has worked as research fellow, Department of Electrical Engineering, Kyushu Institute of Technology in Japan for 2 years. And then he joined as development engineer, ADTEC Plasma Technology Cooperated Limited, Hiroshima, Japan for 5 years, and research associate, Center for Plasma Materials Interactions, Department of Nuclear, Plasma and Radiological Engineering in University of USA. And he has even worked as a senior dry etch R&D engineer, DRAM by EM Micron Technology Incorporation, Boys, for more than 4 years. And now Sir is currently working as senior R&D scientist, the lead scientist on plasma etch development for next generation Intel's Optane technology, Intel Corporation, USA, for more than 5 years. And now we are proudly having a warm welcome to and hand over the session to Dr. Ramraju, sir. Sir?
Yep. Sure. Thank you very much, Dr. Dhanlakshmi, and I really appreciate your introduction. What I do now is I will just go ahead and share my screen, okay?
Sure, sir.
Okay, can you able to see my screen?
Yes, sir. And can you hide the bookmark seen below, sir? A bookmark seen below. Hide.
This one is
No. Can you see a bookmark message at the end, sir? At the end of the PPT slide.
Oh, that
You're
one.
Having start.
Yeah, that one is basically
You can just
slide itself is designed like that. So no worries about
okay.
it. Can you able to see the screen, full screen?
Yes, sir. Yes, sir. Yes, sir.
Awesome. So can you able to hear me very well as well, right?
Yes, sir. Yes, sir.
Great. Okay. Thank you, Dr. Dhanlakshmi, for the introduction, and I'll be starting my lecture today. So basically, today I'm going to talk about fourth state of matter and its applications in various different industries. So at the beginning of the talk, we'll go through what is fourth state of matter, and then in the second part of the talk, I explain more about what are the different applications that we have for the fourth state of matter. Okay, so thank you very much, and I will start my slides. So about myself, Dr. Dhanlakshmi already, introduced me to the audience, but I would like to just give a little more information that, so I'm basically a dad of 2 kids, and currently I'm working as a senior development scientist to Intel Corporation in New Mexico, in United States. So when we talk about Intel, people know that every one of us have laptops, you have electronic devices, you have all sorts of things, right? The desktops. So we all know that Intel makes make processors for the computers and all electronic devices. So at the same time, they also make the memory chips. So my experience in the overall semiconductor industry so far, right? So overall, my basic my background is plasma science. Okay, I got my PhD in plasma sciences, where I started learning plasmas, and then you know I worked on DRAM. We all know that, we're engineers. DRAM, dynamic random access memory. It's a volatile memory, and we also know that NAND. It's another type of memory. It's a non-volatile type memory. And there's a new technology which is coming up that is called Optane technology. So basically, DRAM and NAND, they have limitations of storing the data. So right now, every industry, especially the electronic industry, they are trying to make the processors or the memory chips, as much as smaller possible, and also try to, make it more, efficient, because our data storage needs are actually going up, and also we want computer to run so fast. Our electronic device, if someone turning on the phone, they wanted to have the things moving faster. So, okay, good. So I have been working on Optane technology, and DRAM and NAND are my specialties as well. The memory chips. So basically, as Dr. Dhanlakshmi said, I got my PhD in physics from Bardea University in Coimbatore. After that, I worked as a research associate at the University of Illinois at Urbana-Champaign. And then right now, I'm also acting as a director for some of my own businesses, like solar Shakti panels and Ramalinga Packaging Industries in Sivakasi, where we make solar panels. And also here we make paper products, paper packagings for green energy. So I basically love to listen, Ilayaraja's music and also A.R. Rahman's music. I love to read a lot of, Tamil, ilakyams, especially the one which I'm so much interested is the Karisal Ilakyam, the south part of Tamil Nadu's literatures. So I'm more interested in reading. Whenever I get a time, I read them. Well, I participate in marathon and play cricket in US. So I'll be, moving to the next slide. Okay, let's jump into our subject. Okay, now, so we all know that we have 3 states of matter, right? Solid, liquid, and gas. So this one looks like a simple cartoon where even a school kid, even a kindergarten kid can understand. Well, a solid. So the best example is ice, and then you have when you heat it up, right? When it melts, it becomes water, right? And then when you heat up more, what will happen? It become gas, right? When you heat up, it started evaporating and it became a gas. So we all know that solid, liquid, and gas. There are 3 states of matter. We might have learned in our elementary school and high school level. Okay, let me go to the next slide where I touch a little bit of 4th state of matter. Okay, with some fundamental science behind it. Okay, so look at this. This is a solid, right? you have, you see the molecules in the solid. These molecules are fixed in a lattice, right? It's in a lattice. There's a definite shape, right? There's a definite structure. So if you take a diamond, if you take any solid, it has some structure. Let's take a salt. So this one, the liquid, right? Liquid, where you see the molecules are free to move. But in the gas, you have molecules are more free to move, and they move in a large space, large spacing, right? So basically, the fourth state of matter, which is called plasma. Let's say just you have a solid, you are heating up, and it's becoming a liquid, and then if you give more energy into it, it doesn't matter if it's a heat or the electrical energy into it, it become a gas. And then if you start giving more energy into this gas, right, what will happen? The molecules, right, it get ionized. So what will happen is, look at just an example, right? The ice, so it's H2O. Again, this is the temperature is around 0 degrees centigrade or less than that, and liquid, right? When you heat it up, the temperature is in between 0 to 100 degrees centigrade. The molecules, once it reaches 100, started evaporating, of course. So in between, it's actually a liquid. And then when you are adding up more heat into it, or more energy into it, so it's basically become a steam. So steam, right? So you are keep on giving more and more energy, right? Then what will happen? This H2 will dissociate, right? The H plus and H plus. And then you have electrons. So basically, in a plasma, so far we saw, in the solid or liquid or gas, you have only molecules, right? So in a plasma, what you have is ions, the one which is positive, and then the electrons, as well as you have neutral molecules. So this is a very simple, explanation of what is fourth state of matter. Okay. So now we are just starting now, understanding what is plasma. So one thing I wanted to make it very clear here that this talk, absolutely, when you just go out of this, seminar room, you will be knowing what is plasma, what is the fourth state of matter, how you define fourth state of matter, and then how you define, let's say, how you define for a layman, right? How you define for an engineer what is plasma, and what are the properties of plasma, and then the applications, right? And then after that, I will jump into applications. So my objective is to start with very fundamental science, where people can understand what this fourth state of matter is, and what exactly it does for people, what exactly it does for industry. Of course, whatever the industrial revolution which is coming into us as an application, so it's basically what it helps, what it does to people, okay, and how it improves the life. That's what it is. It's a very fundamental talk, okay. Okay, so let's go to the next slide. Okay, we know that it's solid. Let's say the example rock, and then liquid, and then the best example for the gas is the cloud. And we know that the lightning is plasma. The lightning strike is a plasma. We know that how lightnings are formed, right? So we have clouds, we have positively charged and negatively charged clouds. When they meet each other, we see the lightning. So this is the best example in the nature where you see plasma, right? So this lightning is an example of plasma. Okay, now let's go to the definition, the practical definition. Okay, I'm not going more into the science part. Let's start with, let's start easy. Okay, the plasma is the fourth state of matter. We just saw with some examples, right? The plasma, in plasma, the electrons are unbound from the nuclei due to very high temperature, either very high temperature or a large voltage potentials. Okay, so now we know that plasma is the fourth state, and then where you have electrons, ions, and neutrals, because the electrons are knocked out from the molecules. That's where the state is called plasma. So, and also we know that it's high temperature. So these are all the fundamental things now. Okay, so this is something even for a layman, even for a high school student, right? Just to explain what it is. This is how it goes. Okay, then when we just go and start look at how the gas is different from plasma, right? Well, we just look at some fundamental physics, okay? So the electrical conductivity. So in the gas, right, it's very low electrical conductivity, while in plasma, it's extremely high. Why it's high? Because you have charged particles, right? The electrons are moving around. Electrons are tiny and they really move very fast. It has a high velocity, so on and so forth, right? So you also have ions, the positively charged ions also there. So you have extremely high conductivity there. Okay. So if you look at the velocity distributions, right? Gas, we have molecules, right? We always assume that it's in a thermodynamic equilibrium, right? In plasmas, you have a different species, electrons, ions, and neutral particles with different masses and different charges. Of course, neutral particles don't have charge. Electrons and ions have different charges, right? And different masses. So it has a different speeds. It has a widely different speeds. And when we look at another thing, the interactions, right? So usually in a gas, right, we have one-on-one collision, right? The molecules collide each other because it's free to move, right? In plasma, we have particles, right? The electron, ions, right? So they're constantly interacting with electric and magnetic fields. Why electric and magnetic fields? Just think about it. You have electrons. So when it moves, you are creating electric fields and magnetic fields, right? So the particles are constantly interacting with electric and magnetic fields over the long distances. That's something you need to clearly capture that. So now we know that. So now the plasma is the fourth state of matter. It has electrical conductivity. The species have different velocity distributions. All those things. Now you have some better understanding what it is. Now, the commonality between gas and plasma, neither gas nor plasma have definite form or volume. So there's no shape. Okay. Now, let's go to a little bit more, okay? Definition of plasma. We are still talking about the definition of plasma. So before going more deeper into that, I'm giving a caution to the audience that the plasma in physics, that's what I have been talking about. It's not to be confused with the blood plasma. Okay, good. Now, so look at this. The state of matter, solid, right? Solid. Well, I mean, I'm just classifying where does all these, different matters, fall into the natural system, right? The solid, right? It's the condensed matter. It's compact. It's fall under the nuclear system. So the liquids and neutral gases, follow the Navier-Stokes systems. It's a fluid, right? And then plasmas, of course, the electromagnetic system. So it follows the Maxwell-Boltzmann system, basically. So now the standard definition. I'm going to standard definition because now I started telling the audience in a fundamental way what are the different states, and then how plasma is different than the other states of matters. Now we can jump into a little bit of science, a little bit of fundamental definition. Okay, the standard definition of plasma is as the fourth state of matter, where the material has become so hot that electrons no longer bound to individual nuclei. Thus, plasma is electrically conducting and exhibit a collective dynamics. Okay, here now we can in other words, instead of going too lengthy definition, right? Just say that plasma is an ionized gas. So the state of gas, when you ionize it, then it becomes plasma. Okay, that is the fourth state of matter I'm going to talk about. Okay, now let's go to a little bit of more, natural occurrence of plasma. So the interesting thing is that over 99% of this universe is made of plasma. So plasma is the most common form of matter in the universe, in other words. So in the opinion of many astrophysicists, right, it's the very first state, because they believe that the plasma, it formed immediately after the Big Bang theory in physics. So now the takeaway here is 99% of the universe is made of plasma, and then the rest of the 1%, right, that where we live, and also you will also see, you have a sea, you have a jungle, you have forest, everything. So basically 99% of the universe is made of plasma. That's the takeaway here. Okay, now this is a quiz. Of course, these webinars typically operate in a system where everyone will be muted. I'm not going to run the quiz, but I will go one by one. Where you see plasma in your daily life, where you see plasma at your home. Are you seeing plasma when you are walking around the streets? Are you seeing plasma at your college? Are you seeing plasma at your lab? Let's see. The first one is a plasma TV, right? Well, instead of seeing the plasma here, the plasma TV where you are getting a colorful, nice images and enjoying the pictures. There is a discharge going on in the plasma TV, which is giving you a better image. Plasma TVs is just starting with the one that you have in your home. The next one is the fluorescent lamp. I'm pretty sure every one of us have a fluorescent lamp in our home. That is a discharge tube where you have a cathode and anode. And once you turn on the switch, you see the discharge is happening. And as a result of the discharge, electrical discharge, you are getting the light, right? That's the plasma. Now, the next one is the neon signs. I'm pretty sure many of Chennai people might have gone to the malls, right? You guys have wonderful malls there, Phoenix Mall, Forum Mall, and all those things. So when you enter, when you go to each and every shops have neon signs to just tell the customers that, hey, we are open. And they just want to tell that what is going on there, what kind of discounts going on. You might have seen the neon signs in different colors, the nice, beautiful pink color, blue color, green color, and all those sorts, right? Those neon signs are plasmas. And the lightning, right? Lightning, I already just explained. So lightning is a plasma. It's a natural occurrence of plasma. So if you look at plasma TV or fluorescent lamps or neon signs, those are kind of man-made plasmas applications, right? This is the lightning is a naturally occurring plasma source, right, of plasma. And then the welding arc. Yes, you might have seen when you are walking in your industrial area or busy, streets where people are working with welding arc, joining the metals. I think TIG welding, MIG welding sorts of things in your mechanical engineering lab, or even your workshop where the students started doing some projects. They might have seen that the welding, the arc which is coming out of the welding machine is a plasma. Okay, the big one is the sun, right? Sun is a naturally occurring source of plasma. So sun is a tremendous, source of energy and light. So all those things are coming because the sun's core is very hot, and you are creating plasma over there, and then you are energizing the stars. Of course, you are creating a lot of energy through the fusion reaction, right? Nuclear fusion is happening right there. So sun is the big one. The big boss is sun right now. So the stars, of course, stars, getting energy from the sun and giving us light. So that's also a discharge, which is giving us light, right? Okay. Tesla coil. I'm pretty sure some of the physics students or electrical engineering students, hardcore electrical engineering students, might have studied or seen the Tesla coil, right? In our lab, or trying to do some experiments, because the Tesla coil makes weird noise with some arcs coming out of that. So those sparks or arcs, they are all plasmas. The next one is the fireball of nuclear explosion. So the moment, when India tests the nuclear explosion that you might have seen in the TV when you are a kid or maybe a young adult. So the fireball, which is just emanating once you explode the nuclear weapons, that's also plasma. Just to give a typical example. Now we know that, okay, we have plasmas in our daily lives. You might have seen it. Now that fourth state of matter, I'm moving to the next slide. Okay, so the natural occurrence of plasma, I said 99% of the plasma, our universe is made of plasma. So if you go at about 80 kilometers above the Earth's surface, the atmosphere is no longer made of gas. Instead, it's made of plasma. So if you go 80 kilometers, it's not too far though. It's not too far from the roof of your home, right? 80 kilometers. It's not too far. So everything is plasma. So some of the examples we already saw. So the stars and the sun, solar wind. We know that solar wind is high energy electron beams. This is one of the pictures taken in NASA. I see this, the electron beam right here. This is plasma tail. So interstellar and then space between planets, star systems and galaxies, lightning, auroras. Look at this colorful aurora. How beautiful it is. See different colors, right? The blue, green, red, pink, so on and so forth. Okay, nature is so beautiful, isn't it? The lightning is scary a little bit and dangerous too. Look at the stars. So these are all plasmas. So we are all seeing the plasmas. We are all experiencing the plasmas in our daily lives. Okay, ionospheres, of course, made of plasma. That's about 80 kilometers. It's going to be ionosphere, right? So basically, the closer to home, on the other hand, plasmas are rarer occurrence. Of course, we still have a lot of plasma applications that we might be experiencing in our daily life, but closer to the home, its plasmas are really, really rarer occurrence. Okay, let me move to the characteristics of plasma. Okay, in plasmas, I already said we have ions, electrons, neutral particles are there, right? And they are in equal numbers and making it electrically neutral. So when someone define a plasma, the first thing you need to understand is the number of ions, Ni, is approximately equal to number of electrons and number of neutral particles. Okay, so that means the plasma is in a quasi-neutral state. Okay, so plasmas are affected by electric and magnetic fields. So you can shape the plasma into different forms using or applying magnetic fields externally, and then you can make. I will talk about the application of plasma confinement later, but this is something a very fundamental level. Okay, now in the plasma there are two types. One is thermal plasma and non-thermal plasma. If you look at the fundamental way, a thermal plasma is where the ion temperature is equal to electron temperature. Okay, before going into that, when you talk about plasma, there are few things will repeatedly come in. So one is what is the density of the electrons in the plasma, and number of ions, which is number density of ions, neutral particles. At the same time, each species have their own temperatures. So electrons have their own temperatures, the ions have their own temperatures, and they have their own velocities. So electrons are really tiny, right, compared to ions. So it moves faster. It has a different velocity distribution than the ions. So when you have the plasma where the ion temperature is equal to the electron temperature, then that's thermal plasma. So in non-thermal plasmas, the electron temperatures are always higher than the ion temperature. So when we talk about the temperature, we talk in electron volts. So 1 electron volt is 10,000 Kelvin. So when we talk about the electron temperature, we talk in electron volts. So now we have some better understanding of plasma, right? What is plasma and how you define it, and what is the natural occurrence of plasma, and where are all you see that plasma in your daily life, and where we have a more natural occurrence of plasma. Those are all the things we already saw. So that is good. Now, I'm just going a little bit more into the types of plasma as well in one more slide. So the natural plasmas, right? This is the sun, stars, and clouds, and lightnings. Artificial plasmas, you see the plasma TV and the plasma lamp, right? Okay, now let's jump into a little bit into the properties of plasma. I told about thermal plasma and non-thermal plasmas, right? So we typically, the number density, the number of electron, so we call it as electron density. When we say that plasma temperature, it's basically the electron temperature of the plasma. So we typically see the number density of the high temperature plasmas. Basically, the high temperature plasma example is in the sun, in the stars, or the fusion reactor, the nuclear fusion reactors, where you have a high density of electrons, 10 to the power of 20 meter cube per meter cube, right? And in the non-thermal plasmas, you typically see 10 to the power of 10 per meter cube. So basically, you have a low density. Non-thermal plasmas are low density plasmas. On the other side, the thermal plasmas, the best example for thermal plasma is the arc which is coming out of the welding machine is the thermal plasma, where you have electron temperature is equal to the ion temperature, where you know how much temperature it is, because it's melting the metals, right, and joining the metals. So it's really high temperature. That's thermal plasmas. And non-thermal plasmas are one of the things that I will focus more, because that is something we can make in the lab, we can make in the industrial settings, and we can make use of make use in a lot of applications. Okay. Now, again, the plasma characteristics, just to give an audience, to understand a deeper understanding of plasmas. So look at this. This is the electron temperature, that is plasma temperature, we call it as, and this is plasma density, that is number density of electrons per meter cube in the plasma. So as you see from here, you see the fusion reactors, nuclear fusion reactors, the fusion experiments, or the sun. You have a high density, and the gas discharges that you see in your fluorescent lamp at our home or neon signs have a lower density and lower temperatures. And if you look at the process plasmas, this is where I'm going to focus. Process plasmas, the plasmas which is used in the industrial processing, industrial applications, in the energy, in all other different applications, right? So this is the plasma that I focus more because it has a lot of applications in the industry. Of course, the fusion plasmas also have more, a lot more applications as well. So when we go to here, the next graph, right? What it shows is the pressure and then the power, right? So why we are talking about pressure here? Okay, well, if you want to create plasma, right? We all know that if you go the ionosphere, right, above 80 kilometers, we have a low pressure over there. So once you go up, that's why when you take off in the flight, you sometimes feel, your ears are slightly hurting. People try to chew some chewing gums or bubble gums to get rid that clogging which is going into your ears, right? So it's actually low pressure. So low pressure is very the key thing for making plasmas, because you have to make ionizations, so you need low pressure. Low pressure is the vital one for the plasma, making plasma. Then look at the frequency of the power source. So some of the electrical engineers might already know about this, right? So DC, right? We know DC. We have DC, AC, and RF. It has different frequencies, right? Look at this number. So this is microwave, right? 2.45 gigahertz, and this is RF range power sources, and this is DC. So AC is close by. So basically, we use different power sources to make plasmas, right? Because you need to give energy to the gas which is in the low pressures to strike plasma. That is the idea. That's the concept, right? So if you look at the plasmas, yes, there are several types of plasmas you can make. Electrical engineers know about it, capacitively coupling, right? Inductively coupling. How you couple the power to something, let's say to gas or to some matter, something. So there are several ways you can couple the energy, the electrical energy into different matters, right? The capacitively coupling, inductively coupling, and then electron cyclotron resonance. Those are all the methods you make plasmas. Of course, you make DC, right? DC, DC power can be given to the gas, and then we can make plasmas as well. So the welding arc is a DC arc, and DC glow discharges. And neon signs and DC magnetrons, so on and so forth. So we will go more. We will do deep dive into that. Okay, good. Now we have audience might have a very good understanding of what is plasma and natural occurrences, and also how we define plasmas, so on and so on. Now we are jumping into how we can make plasmas. Okay, now I'm just going into capacitively coupling. Okay, it's called CCP, right? For CCP, what you need, okay, in general, to make a plasma, okay, you have a plasma chamber right here. You are pumping down, you are using vacuum pumps to pump this chamber down, so that you will be, what are you doing basically? Vacuuming. You're sucking the gas out of it, right? And then bringing this vessel into low pressure. Okay? So low pressure, first of all. Then you have the RF generator connected between the anode and cathode. These two are the electrodes. So the moment you started giving a power into a low pressure gas, you still have gas inside. It's not possible to completely pump pumped out the molecules, right? It's tough. So you have a low pressure gas in there. Of course, if you want a plasma of specific type, let's say you want argon plasma, right? You want to make a plasma made of argon gas. You will be, you will be supplying few 10 to few hundred SCCM of gas into the system to make sure that your low pressure chamber is filled with the gas the plasma that you wanted to make. Okay, so now you have power, right? Once you power up, just think about it. One electron, tiny electron guy, it might be coming out of the electrode, or it may be coming out of the chamber wall. So it just hit the molecule inside the chamber. And what it does, those electrons are so fast, and it knock out the electron from this molecule. And it knock out one electron, another electron, and these electrons will go and hit the neighboring molecules and knock out more electrons. This will be happening. This is a kind of cascading effect which is happening in a shorter time. So now you are in a plasma state where you are actually the molecules losing the electrons. So you have electrons, and then this will become a positively charged, right? So if it happens like this, look at the magnetic fields right here, the sign that you see here, right? So now you have electrons, ions, and neutrals. So that is the plasma, where you have a plasma inside the chamber. Now, the making plasma, there are a few things we need to understand. As I said, you have electrodes, and you need to power up. Either it may be DC, it may be radio frequency, or it may be a microwave. Now, you need a pressure 10 to 100 milliliters, and you need a gas to strike plasma. When you talk about the gas to strike plasma, right, different gases have different ionization potential. What is ionization potential basically? So the amount of the energy that needed to knock out a single electron from the molecule, right? So look at this. So helium, neon, argon, krypton, xenon, and radon, right? These are noble gases. So people typically make plasmas using this, where you see the ionization potential is very different. So what does it mean is, so if you have a gas with a lower ionization potential, you may create plasma easily with low power, right? With the amount of power that you feed may be lower. Let's say if we are making argon plasma, if you can strike the plasma with 500 watts, then you may need more power to strike the plasma with helium because the ionization potential is larger compared to argon, right? Okay, now we have the fundamental idea how we can make plasma in the lab. Okay, let me jump into the application parts as well as some of the fundamental things. Plasmas are colorful. Look at this neon signs, right? Neon signs that you might have seen in the malls. So look at these colors: helium, argon, pretty pink color, right? Xenon, the hydrogen vapor, right? Hydrogen, the krypton and neon. So different plasmas have different colors. Where does this color is coming from? Fundamentally, the physics is, so you are actually creating a plasma. You have ions and electrons. So all this ionization and excitations, all those things are happening. In the fundamental physics, so it has every different gases have their own characteristics, wavelength. It emits the light. So when you create a plasma, so you see that characteristics colors. So I'm starting the application. The first application is lighting. This is the big application that we are all seeing in a daily life. Neon signs and plasma lamps and fluorescent lamps, all those are applications of plasma. Now, I'm going into the big one, right? The sun. I already told sun is a big brother. It's really hot, and it has tremendous amount of plasma in it and producing a lot of energy. What energy it is producing? We all know that. We studied in a high school or the first year of engineering physics, the modern physics. Professors might have taught that, fusion reactions, right? So what is fusion reaction? Light atoms like hydrogen fuse together so tightly and they release tremendous amount of energy, right? We have studied, and that reaction is happening in the sun, right? We have studied that as well. So the sun's core is a natural fusion reactor where you have high temperature plasmas, and sun has hydrogen and helium as well, where you have a gas over there and you are at high temperature, you will be generating plasma over there, right? So the plasma basically helps the fusion reaction. So we have a helium. We know these fundamental reactions. The helium, they actually fused together. Hydrogen fused together and then become a helium and produce tremendous amount of energy. You know how much energy it's producing? It's tremendous. It's huge. So 4 times 10 to the power of 23 kilowatt every second. This much amount of energy the sun is producing. So this is fundamental Einstein's law. You can just check my math. This is how it's actually producing. So the sun converts about 600 million tons of hydrogen into helium. So you have hydrogen in the sun, and you have helium and releasing a tremendous amount of energy, and that's really a huge energy. Now scientists are thinking, what if we make something similar reaction in the lab, in the earth? We could able to produce a lot more energy, and they can bring that energy to our home to light up your electrical devices, light up your home. You can use that energy, right? Yes. So the man-made plasma fusion reactors. So scientists all over the world, they're working very hard to make use of this plasma, right, and create that plasma in the lab, in the earth, and create a fusion reaction, and that's called controlled thermonuclear reactions. Why it's controlled? Because plasma, it's in a controlled manner, where we can create tremendous amount of energy. So countries like India need a lot more energy, right? So when we talk about the energy, if we talk about the energy in India, right, most of the energy is coming from where? Most of the energy is coming from gas, coal, natural gases, right? Most of the energy for us is coming from there. And then what else? We have some nuclear reactors as well, producing some energy. And then where else it's coming from? Solar energy, right? So much of different energies. Of course, wind energy. We can talk more energies, but fusion reactors produce tremendous amount of energy, and scientists are still working on it. But still, a lot of progress made. So what they're doing is they're basically making a hydrogen plasma, and then they're using a magnetic field, strong magnetic fields, to confine the plasma in a controllable region where fusion can happen. So in the sun, if you look at it, the sun uses the gravity to get its nuclei close enough and then hot enough to start the fusion reaction. So in the nuclear reactors in the earth, it uses hydrogen plasma, and they use strong magnetic fields to confine the plasmas, and then they do a nuclear fusion reaction, right? So I'm jumping into, this is the biggest nuclear reactor in the United States. It's called tokamak. It's in the Princeton Plasma Physics Laboratory. And then the another one is in MIT in USA. Look at these plasmas. So basically, you have nuclear reactor. People started working. They already built some of the reactors. And India, we are not behind other countries. We are, of course, doing pretty good in terms of building a plasma nuclear reactor. Audience should not confuse between plasma nuclear reactor and the fission reactor which we have in Kalpakkam, or the one we have in Kanyakumari. Those two are two different concepts. Okay, so this is the first Indian nuclear plasma fusion reactors called Aditya. So the Institute of Plasma Research in Ahmedabad, the group of scientists actually working on it day and night. This is the steady state superconducting plasma fusion reactor. You see the proud Indian flag is there. And so this is something, every country wanted to have tremendous amount of energy because need is more and more, right? When I was young, my house had only 3 fluorescent lamps. Now, look at the houses now. Lot of electrical appliances, lot of things. Air conditioning, right? Air conditioning sucks a lot of energy. People need a lot of energy, electrical energy, right? So now, the fusion reactions, right? The plasma fusion reactors. So now we know lighting is one application, and another application, the big application, is the energy, right? The energy sector have a lot of applications in plasma. Now I'm jumping into more engineering side, where the plasmas in the semiconductor electronics, semiconductor industries, right? Semiconductor companies are making chips, right? Not the potato chips, the chips on the silicon wafer, the processors, the memory chips, right? The DRAMs, NAND, and all those things, right? The plasma plays a vital role in the semiconductor electronics manufacturing. So some of the examples are, PVD, the physical wafer deposition, plasma enhanced chemical vapor deposition, plasma etching, plasma cleaning, passivation, and plasma sources for extreme ultraviolet radiation for lithography, for forming a patterns, right? So I will just go into Moore's law. What is Moore's law? Gordon Moore is the founder of the company Intel, right? The Gordon Moore, what he was predicting is that the Moore's law is basically the number of transistors that can be packed into a given unit of space in any electronic devices will roughly double every 2 years. So that means the number of transistors in your processors or the memory chips will double every 2 years. But the size may be same or even smaller. So that is very challenging, right? You have to keep on building, increasing the density of the transistors in your processors, but you also have to keep the sizes smaller, and it's also electrically should perform better, right? That's the fundamental of Moore's law. So what exactly the Moore's law is saying us is the computing power tends to approximately double every 2 years. That's what it is. So if you look at this graph from somewhere in 1810s to until now, look at this. We start with the analytical engine. We have IBM first started making IBM tabulator, and and then you keep on going. IBM made a chip 704, and then you have Apple made the computer, and the Compaq made the desktop. So keep going, right? So if you look at it, every year, whatever the chips that you have in your computer, We started with electromechanical devices, right? Starting with abacus. So we started counting, doing counting machines, punching machines, so on and so forth. And then the revolution is the solid state relay, right? So we had relays. We have a big vacuum tubes, right? The transistor itself looks so big, vacuum tubes, and then the transistor. So the transistor made up, that's the revolution of the electronic industry, where we started using plasmas to make transistors. I will explain that in the slides, okay? And then the integrated circuits, right, where you see the Intel's Pentium 1, 2, 3, 4, and now it's going like core, different cores, right? Core I5, I6, I7, so on and so forth. So keep on going. So if you look at it, the Moore's law, what exactly explaining is you want to have your device tightly packed with more number of transistors, so that you can improve, you can have the better efficiency, better output. So today, all customers' processors, either it's Intel's or Samsung's or AMD's, IBM is not making chips anymore. They are out of semiconductor business. They are more into software right now. So they are out, pretty much out. Just a couple of, a group of scientists doing some fundamental research. So you know what? The second most abundant element in the earth is silicon. That's where all these, the memory chips and all these processors are made in a fab. So the most abundant item is oxygen, right? So silicon. Now, see that this is a silicon wafer where you see the chips right here. Okay, let me go jump into it. So, okay, plasma etch. Plasma etch is the most critical process that we use in the processor making and all those chip making areas. So what is plasma etch? Let's say the substrate, the silicon, that's where we are making patterns, we are making the semiconductor chips, right? So basically the layer to be etched is removed by chemical reactions or physical means, that is ion bombardment. So basically what is happening is you have a silicon wafer and you want to make nanometer trench. Why nanometer? Because as I said, we need to shrink the transistors. We need to shrink the size of the transistors or any electrical device that we make in the processor, right? The capacitor or even a transistor, we want to make it smaller and smaller, and we have to make it more number. That's the whole idea, and make your device performing better. So in order to make that, we need to make nanoscale features. So where plasma is playing a major role, where plasma has ions, neutral, and you have a silicon wafer in the plasma. Just look at it. So to etch away plasma, you start making nano level trenches. You will be using chlorofluorine gas, CF4, for example. You make plasma with it. So when you make a plasma, it dissociates first. CF4 will become C and F, CF, something like that. Then you have a plasma where you have a silicon, it reacts with it, right? You have a neutral molecules, that's the radicals. That's where the radicals, the chemical reaction happening. And then you have ions physically bombard and, the byproduct, right? If you are using a silane, if you are using a silicon, and you are using a CF4 gas, and what you get is silicon fluoride that will be pumped away from the vacuum chamber. So this is how in the industry, plasma etching is making a nano level trenches where you can. This is one of my patterns. If anyone interested, they can go over and see what is plasma etching, how actually it's working in the semiconductor industry. And the next one, you see here the plasma etching. Look at this. We are going into nanotechnology, right? We are going into nano era where we wanted to have everything, have applications of nanotechnology in our lives. And look at this. This is the trench made out of the plasma etch which is 43.1 nanometer, and this is 20 nanometers, and this is 19.3 nanometers. So when you use a plasma to etch away the silicon, make these trenches to make the transistors or the electrical devices, this is the plasma etch is playing more important role. So you can refer to my pattern if you want to get more information there. Okay, now I'm jumping into different plasmas, right? We already saw the capacitively coupled plasmas, and another type is inductively coupled plasma, where we know there are electrical engineers are here, and some of the physics guys might be here as well, and so we all have an idea how this inductively coupled works, right? You have an antenna, you are powering an energy, either it's RF, microwave, and you have a dielectric window, a glass window, and you have a plasma chamber. So you are pumping down to low pressure, and you are creating a plasma by inductively coupling the power and making ionizations. And you see the plasma right here, where you see the silicon wafer sitting there. So this is one type, right? And another one is, you have an antenna sitting on top. This is a kind of, a coil type. You have an antenna here, you are inductively coupling to the gas in the low pressure and making a plasma. And then another one is you have an internal coil where you power up the coil and make plasmas. So there are several ways you can make plasma. All these plasmas are actually used in the semiconductor industry. And you just look at the schematic of ICP-H system, where you have a coil and you create a plasma right here, and you have a silicon wafer sitting down here, and then you have a E-chuck. This is where you have a plasma wafer sitting, the wafer sitting, and then you create a plasma and make all these small features, the nanoscale features here, there. Now, the another type of plasma that is the commonly used in semiconductor industry is electron cyclotron resonance. What is electron cyclotron resonance? Here we use a microwave. So microwave is coming at 2.45 gigahertz. You see you have a magnets, right? So what these magnets do, it helps, creating a resonance right there. How? For ECR, the DC magnetic field, which is coming from these magnets, the electron, if you look at the fundamental equation of electron cyclotron resonance, right? Electron cyclotron resonance, QB by M, where Q is a charge, B is a magnetic field, and M is the mass of the electron, right? So what happens is the electrons are accelerated so fast if the frequency of the microwave that you are feeding in matches, the frequency here in the magnetic field. So basically, you are accelerating the electrons and making more collisions and making more ionizations and making more plasma and high density plasma. So this is where you have a silicon wafer sitting down here and doing a semiconductor processing. So now ECR versus ICP, just a difference is, you have a coil, you power up with RF. Here you actually use microwave, and you have magnets to accelerate your electrons, and then make a plasma, high density plasma here, and then bring it down to the silicon wafer and do whatever the magic you wanted to do. So this is something very common, fundamental etch types that we have been using. Now this is a ECR plasma, as I said. Microwaves are basically transferred through the waveguides with 2.45 gigahertz and make a plasma inside that I explained. This is some schematic of ECR etcher. Now, I'm done with this etching business. Now I'm going into the PVD, the thin films. So the thin films, basically, the sputtering. The sputtering basically uses plasmas to create thin films. Look at this plasma, nice argon plasma. So what is the mechanism here? Well, you will be creating plasma inside argon plasma, where you have the material that you want to deposit. You have a target right here, and then you have a substrate somewhere here. you are depositing it. How we are doing it? So we know that plasma have ions, electrons, right? So the argon ion, we are making argon plasma. So the argon ions are actually knocking the material substrate that you have here. And then are hitting the surface and then knocking the material, the atoms. For example, you want to deposit silicon for SiO2, or let's say you want to deposit some metals, right? You want to deposit the gold, for example, right? You want to make a gold coating. So you need to have a gold target right here, and you make a plasma, and then it knock up, and then it actually knock out the atoms from the target, and then those atoms will go and adhere into the substrate right here and make a coating. Okay, this is thin film applications, films. It's really a thin film. So one of the applications that I was working, it's actually using the sputter system to make solar panels, flexible solar cells. This is a triple junction, amorphous solar silicon, where you have a NIP, NIP, and NIP. You have a 3 junctions, right? That's why it's called triple junction. So you can make NIP using these kind of PVD, PECVD films. And this is one of the, look at the picture. This is a flexible solar panel that we make, where you can just, fold it, right? You can keep it in your backpack. And if you want to charge it, when you're going for a trekking, you are going a remote place, you can use it. So that was the application, right? So the most common films people use in the industry is SiO2, TiO2, TCOs, ITO, and zirconium oxide. This is one of the patterns. If someone interested, you can just go ahead and look at it. This is my patent. Okay. Now I'm going into nanoscience. People are so much excited about nanotechnology and nanosciences. So plasma plays a major role in the nanotechnology, right? This is a carbon nanotube. So we all know that carbon nanotube have a lot of applications in the electronic industry or materials industry. So this is a typical nanotube made in a DC plasma with C2H2 and NH3. And this is C2H4 and NH3 plasma, where you see really dense carbon nanotubes are made in the plasma reactors. So once you create this plasma in the plasma chamber, the reactions, you can form these carbon nanotubes. So this is nanoscience. And then look at this another example where the plasmas. Okay, before going into that, I have to explain a little bit more. So far we saw that we have an idea that plasmas can be made in a low pressure. You need to create a vacuum. Yes, there are applications for plasmas made in the vacuum, low pressures. Of course, there are plasma can also be made in atmospheric pressure, where we call it as atmospheric pressure plasma or low temperature plasmas. So some people call it as non-equilibrium plasma as well. So I'm jumping into the applications of plasma where you can make in an atmospheric pressure. So there is the advantage of atmospheric pressure plasma is you don't need expensive pumps to evacuate your chamber, to create a vacuum in the low pressure. So you can have a very simple system where you can create a plasma between the electrodes by powering up DC or RF. So here this example is an RF. So you basically create a plasma right here, a smaller volume plasma, and use a helium, H2, and CH4 gas. Then you will see you have this carbon nanotubes formation. So these are all interesting applications of plasma. Look at this, very interesting. This is a capillary tube. This is a 100 micron diameter. So you are flowing argon silane gas in this capillary tube, and this is the cathode and this is the anode, where you can powering up, you can create a plasma. These plasmas are atmospheric plasmas. It's called microplasmas also. So it's a really tiny plasma where you can create a nanostructures, nanoparticles. So argon and silane gas feeding into it in plasma, it's a good chemical medium. Plasma is a good reactive medium since you have reacting particles like ions and electrons and radicals. Radicals basically create chemical reactions, and the ions help on those reactions. So this is ion assisted reactions happening, and then you're creating the nanostructures. This is one of the fluorescent silicon nanoparticle. You can make it with this plasma reactor. Now, this one something some of the mechanical engineering graduates or mechanical engineering professors might already know about this. The plasma spray coatings. How it helps? Well, the plasma spray coatings are special purpose coatings where you have special applications, right? You are working, your parts are, let's say, your parts are working in a high temperature, and you have a more wear and tear where you have a constant motion. So these coatings are very much, plasma coatings are used in the industry. As you see here, the thermal plasma is coming out. It's actually coating the material. How it's coating? So you are actually creating a plasma between cathode and anode, and this is the plasma jet coming out. And what you are doing is basically you are feeding the material that you want to coat into the plasma, and plasma is get melted because the temperature is very high, and then it started forming the coating right here. So this is the typical example. Look at this, the turbine nozzle, right, of your jet engine. You see, after several days of life, you see how much of wear and tear you see here. So this is the chromium coating made of plasma spray, where you see how beautiful it is. And this will actually, the whole idea is to increase the lifetime of your parts, reduce the cost and all those things. So this is the textile parts, titanium oxide coating. This is made of plasma spray. And another application is in the medical field. People who get really severe injury in an accident or something, they break their bones or something like that. The implants, right? This is mostly the hip implant. This is completely plasma coating. And the interesting thing about this, scientists are saying that the tissues even grow on this plasma coating. It's even acting as your bone. So this is titanium oxide coating for the hip implant applications. Look at this colorful picture. Look at this, all your gears and molds and all those brackets and all those things are inside the plasma. Why we have to put it inside the plasma? To increase the lifetime. So this is one of the concept called plasma nitrating. So when you have all these parts inside the plasmas, the nitrogen plasma, so the atomic nitrogen is actually impregnating into the surface of your parts and making your parts more stronger. This is happening in surface level, in a micron and nano level, and make your surface more and more harder. And it actually reduces the cycle time, controlled growth of surface, eliminating all kind of defects, pore-free surfaces, so on and so forth. So it's basically, plasma has so much of applications. This is one of them. It's a surface modification. You modify the surface you want it to be. You make it more stronger. You make it the longer life of the parts. Okay. So the environmental applications of plasma. Yes, we do have a lot of environmental applications. So the one is plasma gasification. What exactly is this? Basically, you have plasma, which is the high temperature arc. So you are heating up the waste. You are heating up the waste. You are burning it, and then making it a rocky solid waste. And those are, honestly, a lot of those rocky solids are used in the United States as building materials. Now, supporters even claims that it is cleaner and greener after you treat with plasma. And another issue, the medical waste. This is the big problem in India, right? Every waste are dumped in one place. We don't know how infectious it is, that spreads bacteria and viruses. So this is a plasma system. It's a tall one where you have a plasma created inside, and you have medical wastes are completely burned into like ashes, and then it's actually treated. So basically, mechanism is, first, the plasma, high temperature, and it kills. It actually get rid of the infections as well, and also you are actually ashing it up and then burning it basically. So when you look at it, 79% of the waste are coming from us. We are culprits, human beings. We are actually making the waste. We are throwing the stuffs all over, and some of them are, medical waste. Some of them are coming from the industry. The general waste are coming from us, right? And some of the, incinerator ash and the medical waste and all those things are coming from different industries, medical industries, hospitals, and other foundries, and all those things. So plasma have applications in the environment as well. The aerospace application that I'm jumping into. Look at this beautiful satellite, right? You have solar panels. Solar panels is the only viable power source in the space. You don't have anything else. You can't, build a big power supply into a satellite and make it happening. It's so heavy, right? Okay. Now, look at these solar panels and look at this. What is this? This is something called a thruster. So this thruster is a plasma. So thruster is most important part of the satellite system, where it helps to keep the spacecraft. It helps to keep the satellite in the station keeping. Let's say your satellite want to be in the north-south direction. These thrusters will help keeping them and get the enough information that we wanted. And another application is the jet propulsion. You might have seen the jets. They're all using plasma thrusters. So this is the plasma. You see it's coming out of this thruster. So aerospace applications. Now, I'm jumping into some of my steps, and then I conclude my talk. So this is one of my inventions, right? This is the atmospheric pressure plasma that in early 2000s, there were almost less to none atmospheric pressure plasma in the market. So this is one of my inventions, which is actually, I actually developed a coaxial type microwave plasma system. This is the patents, got it in Europe, Canada, Korea, and China, and different countries. So look at this. You can touch this plasma. So the atmospheric pressure plasmas have different types. Arc welding is also atmospheric pressure plasma. You can't touch it. It burns your hand, right? But these atmospheric plasmas are low temperature plasmas where you can touch. So you know what? One interesting thing I want to tell about this. We originally, developed these plasmas for the surface modification. Let's say I want my surface to be more hydrophobic or hydrophilic. Plasmas can help. What it does, plasmas, when you expose the plasma on the surface, the mechanism is it cleans up the surface. It cleans up the carbon, for example. It cleans up the mud or whatever, the grease, oil, or whatever. It cleans up. And then your surface will become clean, and your surface is activated, and it get more activation energy, and thus, it actually become more hydrophobic surfaces. So just think about it. In the airplanes, the painting and finishing looks so beautiful. How does that happening? Before they do anything, painting or anything, they treat with plasma to make your surface more clean and more looking more better with activated surfaces. When you started painting it, it actually stick very well. It adhere very well and make a very nice coatings, nice paintings. So plasmas are also used in a paper industry, painting industry as well. So this is one of the examples This is the sample we got from the top, car manufacturing company. But they had a secret material. They want to improve the property of the surface. So look at this. Just 0.5 seconds of plasma treatment. Look at the contact angle. So what is contact angle? So this will tell us whether your surface is hydrophobic or hydrophilic, right? So if you have a surface, normal surface, when you put a droplet, water droplet, you always see something like this. But when you treat it with plasma, it will be flatter. The contact angle is 0. So that's what you see here. The contact angle is 0 after treating your surface with 0.5 seconds. So improving the surfaces. So what happened is, while I'm developing this, while we are making a plasmas in the lab, a secretary from our lab just came, and then we were just telling her that, hey, we made a cool plasma. Do you want to touch it? Yes, he said, yes, of course. She was just touching, this is the picture you see here. She was actually touching the plasma for about 30 seconds. And then next day she came and she was telling us that, hey, yesterday I had some cut in my finger where the plasma was exposed. And now I feel like, it's that cut is healed. So some plasma is doing something. It's healing something on your wound or cut or whatever. Then we started thinking that how the plasma is helping on wound. Yes. So what we did, we actually collaborated with the hospital where we got bacteria, right? The E. coli bacteria. This is E. coli bacteria, as you see from the hospital. So this is one of my patents. Of course, so anyone interested can just go and look that. So we had 10 to the power of, we have like 7,000 counts of bacteria here. So we started exposing with plasma. You look at this, initial and control, and we used plasma and also UV. So ultraviolet rays, right, also kill plasma. The diamond thing, this is basically, you see here, even though you expose to 600 seconds, you still see some bacteria. But you see the miracle, the plasma, when you expose it, bacterial density started dropping and then going to 0. So look at this picture. At the beginning, after 5 seconds of plasma exposure, almost gone. 30 seconds, it killed everything. So we understood that plasma is killing the bacteria. So what is the mechanism though? Can anyone guess? Well, the ion, right? You have ions, right? So ions have high energy. It bombards on the surface of the bacteria. The first thing it does is it just rupture the skin of the bacteria. Then it started rupturing the RNA, DNA, whatever. So it actually physical bombardment of ion killing it. Plus in the plasma you have ultraviolet lights, and you also in the plasma have radicals, right? The neutral particles. That's actually very reactive to this the RNA and DNA material of the bacteria, and then finally it kills the bacteria. So it was a very interesting application. We never thought to see application in the medical side, but the plasmas have. This is a kind of invention that came accidentally when someone exposed with plasma and started saying that it's healing. Okay, now the plasma, the commercial systems are available in the medical field, helping the killing the bacteria, as you see from here. And these are the systems, like sterilization systems where you can clean your hand. Okay, now somebody's thinking that why can't we use this plasma in this corona pandemic? You can clean up your hand. You can clean up something that is bothering right now. So plasmas, yes, definitely. This is one of the hand cleaner that we developed, and this is the plasters and all those things. Yes, now plasma sterilization, right? Right now, the people at the University of Michigan, they are actively trying to use the plasma for sterilizing your masks. that you are wearing for corona pandemic, the gowns, and reuse them. So plasmas definitely help. Some of this corona pandemic situation right now, scientists are working on that. Now, I'm concluding my talk. Before that, yes, before going to, before, concluding my talk, I really want every one of us to be safe. Please. Corona pandemic is killing us all over the world. Now in India, right now, Tamil Nadu have more than 30,000 cases. India have more than 2 lakhs cases. And I don't have to tell about the United States. You might be all seen in the TV. It's getting worse and worse. The most important thing is, right, be safe and make your kids and family members, elderly persons, everyone safe. Don't get panic. Don't get panic about like staying inside home. It's good for you right now. So please, wash your hands very well. Keep a social distancing, and I don't have to preach everything here. Don't touch your eyes and nose and mouth with unwashed hands. Wear masks. Try to avoid to go to the crowded places. It's okay. You can go to weddings. You can go to the other things later. Right now, stay safe and keep yourself safe and make sure you are having a good eating habits. Don't try to travel right now. Still have enough time to travel in the flights and all those things. So please stay safe. And I really want every one of us to just pray for 1 minute for the COVID-19 victims all over the world. Okay, the time starts now. Thank you. Okay, thank you very much, all. And I would like to thank Mr. Sriram, Chairman of CIT, for giving this opportunity, and my sister and my friend, Mrs. Sridevi Sriram, Secretary of Chennai Institute of Technology. And I thank Balamurali. We have been contacting each other a couple of times in these weeks, and then he have been very good, smoothly, arranging all the things in a professional manner. Thank you, Dr. Balamurali. And finally, I thank Dr. Dhanlakshmi, Professor CSC, for organizing this. And thank you very much for everyone. I know that I took a long time, but I feel like it's worth, sharing this information here. Thank you very much.
Yes, sir. Thank you for the wonderful session, sir. So, can we have few questions from the participants side, sir?
Yeah, absolutely. Please ask questions. Let me see. Do you want me to go
So,
to?
I have summarized. Yes, I have summarized your questions.
Okay.
Yes, sir. So, what are the updates on the latest studies on BEC? Is it isolable in a laboratory condition? Can you suggest new points on this topic?
So when you say BEC, what is that?
Uh, so they have mentioned like that. So Bose-Einstein condensate. So as per my knowledge,
Okay, both Einstein. Okay.
Bose,
Yeah, good. Okay.
yes, Bose-Einstein. Yes, sir.
Okay. Okay. Yeah, this is more of fundamental physics. Yes, there are labs, working on it, and a lot of people working on the particle physics side on those subjects. But not very much of application on that specific Bose-Einstein system right now. But still, people who have interest in hardcore physics, they're still working on it.
Yes, sir. Thank you. And are the plasma fusion reactor and nuclear fusion reactor same?
That's a good question. Yes, the plasma fusion reactor and nuclear fusion reactor are same, but nuclear fission reactor is different.
Okay. So, what utility required for confining such a high temperature for plasma?
So the question is, what utility? I mean, what is the power
Yes.
needed, right?
Yes.
So to make such a plasma, you need definitely a tremendous amount of energy. It starts from anywhere between kilowatt to gigawatts or something like that, depending on the plasma. If you go to fusion plasmas, typically gigawatt level powers, even less than that. But if you want to confine plasma in the lab, what you need is a kilowatt level. Let's say you want in the welding arts, right? You need the power that you need is like 10 kilowatt, 20 kilowatt, something like that. So it's depending on the application, the power varies. Of course, the nuclear fusion reactors use tremendous amount of input power to make plasma and confine it.
Yes, sir. So, next question is there any plasma coating be done on gas turbine blades?
Yes, exactly. I actually showed one of the examples where the nozzle that is actually a turbine blade. So the best thing will be titanium oxide, chromium oxide. Those are all the coatings, good for the high temperature applications where you can preserve the lifetime and you can avoid wear and tear situations.
Yes, sir. So, and next question, may I know one commercialized plasma product and the cost of the product?
Sure. I mean, depending on when you say commercialized product, depending on what you need. Let's say you are looking for a commercial plasma system where you want to generate plasma in the low pressure. Definitely. I don't know how to say in amount in Indian currency, but definitely the plasma system need power sources, vacuum systems, plasma chambers, so all those things. So if you want to have a sophisticated system with all pressure controls, gas controls, and temperature controls, definitely I would say anywhere between 30 to 50 lakhs. That is for the vacuum plasmas, right? But if you want to have a plasma spray system that you want to make coatings, right? Where you may need like 10 lakhs to purchase that system.
Okay, sir. So, what is the difference between plasma and arc?
Yeah, sure. So arc is itself is a plasma, but when you say the low pressure plasma and the arc, the difference is so basically in the arc, you have more number of electrons and ions compared to the low pressure plasmas, and your neutral gas temperature, meaning the temperature that you feel is so high in the arc compared to the low pressure plasmas or low temperature plasmas where you can even touch the plasmas. So basically, those are two different plasma, different types of plasma. One is thermal plasma, that is the arc discharge, and another one is the low pressure plasma. So if you look at it, how you make it, the arc welders typically need more current than voltage. But the low pressure plasma uses less current and use high voltage. So basically, when you use a more current, that means it's more hotter and it's more erratic, and you need to be very careful.
Yes, sir. So next question, what is the main difference in RF and DC plasma? Is it only about low and radio frequency?
Um, well, in RF plasmas, people have been using different frequencies, of course. So DC, we know that. We know what is the frequency for DC. And, RF have the most common frequency is 13.56 gigahertz. But people also use ultra high frequency where they go 56 megahertz, even they go 110 megahertz. So when keep going, right, they reach microwave where it's 2.45 gigahertz. So people are using a wide range of RF frequencies for making plasmas, but the most common commercially available frequency power source is 13.56 megahertz.
Okay, sir. So next question, which domain engineers can take part in plasma technology? That is,
Wow, awesome! This is a excellent question. You know
this
what?
is my
Yeah, as I show in my applications, right? Whoever have interest in plasma can, because we have a lot of applications. You saw mechanical engineering applications, coatings, the aerospace applications, right? And electrical applications, and we saw chemical applications and environmental sciences, fundamental physics, and also you saw medical applications as well. So plasma is something anybody can. I mean, any discipline can. Physics, chemistry, or from all engineering people. I don't know. Computer science may not be interested or may not be useful, even though their computers, chips, all those things made of plasma processes. But
yes,
fundamentally, if you just take out the computer sciences, all other people in the engineering field, in the fundamental science field, uh, can do a lot more with plasma. If they wanted to do research or if they wanted to develop new applications, yes, absolutely, plasma is kind of area where engineers and scientists can, spend a lot of time if they have interest.
yes, sir. So and next is can you give some idea about plasma therapy, plasma medicines, and
Right.
scope of plasma in the biomedical field?
Exactly. Yes. So you saw some of the applications in the fundamental level. Plasmas can kill the bacteria, and plasmas can be used for sterilizing. So if you look at the applications, yes, one of the applications I can tell you that I know that the endometriosis is a very common problem in the human beings, where there is a systems using an organ plasma coagulation. So what they do is basically same thing like a laser plasma, lasers, right? So these days, people are using lasers to treat your surgery and body parts and all those things. So there is a plasma coagulation system that actually treats the endometriosis, for example. And some people are using even a plasmas, microplasmas to clean your teeth, something like that. In the biomedical applications, yes, there are a lot more applications in the biomedical field. One of the examples you saw, like the cleaning your medical wastes. How you can make it, ashing it and make it as a useful product. So those are all the biomedical applications. Now, but people are trying to use plasma for corona as well. So there are some researches going on, especially the atmospheric pressure, low pressure plasmas, to sterilize or clean up your some of your medical parts and your gowns and masks and all those things. Yes, plasma have a lot of applications coming up in the medical field, biomedical field as well.
Yes, sir. And we'll take up two more questions, sir. Can you give some idea about human plasma donors?
Oh, I'm. That's why I was cautioning in the beginning that the plasma in physics is different than the blood plasma. So I'm not a blood plasma expert. I'm a plasma scientist, where which I talk about the physics. I don't know about that, but that's why I was cautioning people will confuse about it. In one of my slides in the beginning, I'm saying that guys, please don't confuse between the physics in plasma and the blood donors. I wish I could know the answer for that. Sorry, I don't know.
No problem. Which color, is there any color for plasma energy?
Yes, absolutely. I saw. I just showed different colors for the plasmas, right? So every, when you go to mall, right, you see the neon signs, right? In front of every stores, you have, some symbols with a lot of different colors. So you might have seen green, blue, red, yellow, different colors. So those are all different gases in the low pressure filled inside that glass tube. So every gas have different characteristics. It emits the light at different wavelengths. So yes, absolutely, plasma have different colors.
Yes, sir. So, last question. What is the role of plasma technology in farming and global warming?
Oh, nice. In agriculture, right?
Yes, sir. Yes, sir.
Um, yeah, that's a very good question. I was also, thinking about it, but we have a very less applications in that area. I would say very remote uh, applications people are using in the farming. I don't see any, any significant applications in that area.
Okay, sir. And many participants have asked about your site to see your patterns.
Yeah, sure.
Site link. You can type in the comment box below, sir, the site link.
Okay.
Uh,
So where is so you mean the chat window, right?
Chat window. Yes, sir. Send to everybody, and you can type your comments below. The
Okay.
site link to see about your patterns.
Yeah, I mean, once they basically, um, just type the pattern number, they can
Okay.
easily get it. So let me do one thing. Let me go back to my slide and copy and paste. That's one thing. Or
Sure,
maybe,
sir.
what if I just give me a moment?
Yes, sir. You can share your screen, sir, now, if you want.
Oh, yeah, sure, sure, sure. So what I do is basically, you can just um, okay, let me go back here. Oh no, no, no. Mhm. Sure. Okay. Let's see. Controls. So that is one of so what I do basically is I just share the screen. Whoever interested, they can just write down the number. Will that be okay?
Yes, sir.
Okay, the one you can see here, US 20100151
You can
39.
share your screen, sir, as you
Oh,
did earlier. Yes,
they didn't scare my screen. Okay, sorry.
yes, sir.
Okay, okay, we got it. Okay. So, okay, let me share my screen, and then people can see it.
You can even copy the link and put it in the comment box, chat box,
Okay.
if
So,
possible.
yeah, I would say, since it's here, they can write down.
Yes, sir. Yes, sir.
That will be much easier. So the one is US 2010015139 Um, so that is one. and they can also go and look at, oh, the another one is US patent 20110180393. So US 20110180393. And then this one, so you can write the European patent number 1734798, and then the Canadian patent number 2561657. So again, EP 1734798 and CA 2561657. And okay, looks like this one is this one I moved it. Did I? Okay, yeah. Those are all the items that I. Okay, this one is world. So you need to go and search with the World Intellectual Property document. So W/O/2007 /023547. This is on the medical side. So good. So yeah, these are some of the few of the patterns list there just listed. So if someone is interested in looking at more, I can share. But this is something related to plasmas. Okay. So let me go back to the screen right here. Okay. So okay. So what I'm suggesting is if you have more questions, please don't feel to put it right now. I'm okay. I can spend another some time to answer everyone's question. So if you have any other questions, please go ahead.
So we have been posted with one more question, sir. Surface coating process has been used for a long time, and is it effective to prevent corrosion in materials? If
Yes.
possible, with some examples.
Yes, absolutely. So one of the examples someone asked, like in the turbine nozzles, where you have a high temperature, right? So you also have environment where the parts work at the highly corrosive environments. So the best example is the glass industry, right? So if you look at the glass is more corrosive, where glass making process have all the molds and everything, jigs and everything is made of metal, right? Where you have more corrosion happening. So I think in the past, I used silicon, silicon titanium nitride is one of the best coatings that I used for corrosive. I used PVD, physical wafer deposition, to make the coatings. Yeah.
Yes, sir. So that's all, sir. We have covered almost all the questions from the participants. And
Great.
we are very happy to have a great session from you, sir, and having patience to address all the questions from the participants.
Okay.
Definitely,
Thank you
you
very
made
much.
this session more informative, and
Yeah.
you created an awareness of emerging plasma technology. And we really feel interesting to progress the pace of technological innovations in plasma technology in future.
Mm.
So, on behalf of Chennai Institute of Technology, we thank you for spending a valuable time.
Okay.
Thank you,
Thank
sir.
you very much, Dr. Dhanalakshmi, and I'm glad to hear that it's informative and future technologies, and a lot of us started learning something new. I'm very happy about it, and thank you very much once again for all the audience and also the the management and also Dr. Balamurali and Dhanalakshmi for doing all this good work. And I really wish, in the future, if you guys need more speakers on talking about different topics, I'm happy to do that. Thank you very much, one and all, and we will keep in touch, and let's see, how this Corona thing is going to go. But my advice one last sentence I want to say is, please stay safe. Thank you very much.
Thank you, sir. Thank you. And participants, you will be receiving your e-certificate and feedback link to your registered mail ID. And you can check in our college website for the upcoming webinars, online programs, international technical seminars, and various other events. And thank you to all the participants on behalf of Chennai Institute of Technology. Thank you once again, sir. Thank you very
Thank
much.
you. Bye.